Hillary and Carrie, and our topic is Gaussian elimination. But before we discuss that, we would like to tell you a little bit about the systems of equations so that you can understand elimination. The objective of this is to obtain for one of the variables coefficients that differ only in sign so that adding the equations eliminate the variables. Some examples of this is by adding these two given equations to eliminate the x variables and solve for y. Once you solve for y, you can substitute y back into the equation to solve for x.
Okay, when you add these two equations, the x variables will be canceled out because 3 and negative 3 equals 0. But when you add 5 and negative 2, you're left with 3y, and when you add 7 and negative 1, you're left with 6. So 3y equals 6. And when you then solve for y, you're left with y equals 2.
Another example of this is by back substituting x or 3/2 so that you can complete the solving process by solving for y. When you add these two equations, the y's cancel out and you're left with 8x equals 12. You would then solve for x by dividing 12 by 8, which leaves you with 3/2. You can then substitute 3/2 into either of the two equations to solve for y. If you have two equations where the coefficients of the differing signs are different, like this equation, you would take 3x minus 3y equals negative 7 and 3x minus y equals negative 5. Notice that the y variables have different coefficients and signs. Multiply equation 2 by 3 to obtain the necessary coefficient to eliminate y. Then use back substitution to solve for y. So you would take 3x plus y equals negative 5 and multiply that by 3. That gives you 9x plus 3y equals negative 15. You would take that by the first equation given, which is 2x minus 3y equals negative 7, and add those two, which gives you 11x equals negative 22. The product of that is x equals negative 2. This is a no solution case. An example of this is, in this you want to obtain the necessary coefficients of differing sign, multiply equation 1 by 2. This is a lot like the example we just did. You would take the first equation and multiply that by 2, which gives you 2x minus 4y equals 6. You would add that to the second equation, which ultimately cancels out the x variables along with the y variables, making 7 equal to 0, 0 equal to 7, which is a false statement because 0 can't equal 7. Okay, now we have a many solutions case. An example of this is a lot like the last two equations we did. To obtain the coefficients that differ in sign, you multiply equation 2 by negative 1/2. So again, you're just going to multiply 4x minus 2y equals 2 to negative 1/2, which gives you negative 2x plus y equals negative 1. And when you multiply that by the first equation, that cancels everything out, which equals 0, which is equivalent to infinite solutions.
Okay, now we're going to talk about row echelon form. In row echelon form, methods of elimination can be used in systems of linear equations with more than two variables. The goal is to rewrite the system in a form to which back substituting is applied. Also, if a system is in row echelon form, it is in a stair-step pattern with leading coefficients of 1. For example, these three equations, you can see the stair-step pattern. Now we're going to talk about Gaussian elimination, or in Dave's words, elimination. So two systems are equivalent if they have the same solution set. If a system is not in row echelon form, you would first convert it into an equivalent system that is in row echelon form. Okay, for example, if you were given these two examples, which is x minus y equals 0 and 3x minus 2y equals 1, the x and y, since they both have 1, they are both able to, or you can cancel either one of them out. So, for example, what we did was we multiplied the first equation by negative 3 and to cancel the x variables out. You could also multiply the first equation by negative 2, and that would eliminate the y's out. So when you multiply the first equation by negative 3, you are left with negative 3x plus 3y equals 0. When you add that equation to the second equation, which is 3x minus 2y equals negative 1, the x's are canceled out, and you're left with a y and a negative 1. So y equals negative 1. You can see the first equation and the y equals negative 1 put together is in row echelon form. You would then use that negative 1 to back substitute into either one of the equations and solve for x.
Example 1.
Easy peasy lemon squeezy.
Alright, you're given 3 equations in a row. You want to take those the coefficients of those 3 equations and put them into a coefficient matrix, which is this. You would then add row 1 and row 2 together, resulting in this, and giving you the leading coefficient of row 2 to equal 0, which is what you want. You would then take negative 2 and multiply that by the first row, giving you negative 2, 4, negative 6, and negative 18. You would then add that row with the third row, and that gives you, again, a leading coefficient in row 3 to equal 0. Because 1 and negative 1 are coefficients of the same coefficients of different signs, that's going to equal 0 if you add them together. So you're going to want to add row 2 and row 3 together. And that, like I said, gives you a 0, which leads you to have your row echelon form that you're hoping for. You would then take 1/2 and multiply that by row 3 to give you 1 for z, which makes z equal 2. And so then you can take 2 for z and plug that into your other equations so you can solve for x and y.